Hello everybody, and let me start the presentation now. My name is David Raimon. I'm based in Prague and hosting the webinar out of here. This is the second session of Hartmut Jaeger's presentation today. I want to mention that Diggs company is sponsoring this presentation, and I want to thank for some financial contribution towards this happening. And the speaker today is Hartmut Jaeger out of Heidelberg. Hartmut gave a previous webinar on vitrinite reflectance measurements, and today he's talking about optical Kerogen analysis. And I found the morning session quite interesting and eye-opening in some respects. So I hope it will be interesting for you too as well.
So as David already told you, we will talk about Kerogen analysis, new ideas on Kerogen analysis, and see if this is really new wine in new skins or maybe just old wine sold in new skins. I hope you will follow me and understand in the end that it's really something new that I propose to you today. And you just start with the next slide. So what is Kerogen? So first I will give a short introduction. What is Kerogen? What are we talking about when we talk about Kerogen? I will make a short trip through the standard analysis, geochemical analysis, what you might be mostly familiar with, all of you, if you're working in this business. And then we will turn over to the other part, the optical analysis, which might be not so well known by most of you, or maybe not known at all. And then we will have some case studies in the end to show what is the impact of this optical analysis in exploration studies. So Kerogen et al. Was introduced as term by a British geochemist, Alexander Graham Brown, in 1906, so pretty old term. And it comes from the Greek, wax spurs. So this is the material where the wax is born out. And this gives us some idea. So it's something that is related to hydrocarbons, to wax. And what is Kerogen exactly? It's a solid organic matter in sedimentary rocks. So we have two groups of organic matter in sedimentary rocks. We have the soluble organic matter, which we call bitumen, and we have the solid insoluble organic matter, which we call Kerogen. So it's insoluble in normal organic solvents. And it has not a specific chemical formula because it's produced or it's originated from totally different sources, totally different organisms. So we can't expect a specific chemical formula. We have very different chemical formulas. And that's the reason why the same stuff, Kerogen, produces so different hydrocarbons. And it gets originated from terrestrial and marine plants or organisms, and mainly terrestrial plant debris and algae stuff or other planktonic stuff. And during heating, it forms liquid and gaseous hydrocarbons, so it produces oil and gas, and that's the reason why we are interested in. Otherwise, I guess no one would be sitting around the screens now and listen to me talking about Kerogen. So what is Kerogen? Where does it come from? We have the two major sources of terrestrial, geological systems in this globe, the marine and the terrestrial, and both areas in both environments, Kerogen is produced. We have a huge list on the marine side on the left with different types of planktonic organisms and also zoomorphs. So this means clasts from bigger micro or also macro fossils, which are made of organic material. Then we have on the terrestrial side, spores, pollen, and plant debris. And particularly plant debris is a huge contributor to the Kerogen, also in marine and non-marine depositional environments. And then we have the group in the middle, bacteria, algae, and fungi, which is a sort of this and that. We can have it from purely terrestrial lacustrine systems up to marine environments. So this is a group that can be present almost everywhere. And besides the paleoenvironmental control, we also have a stratigraphic control on the type of organic matter that we can store in the sediments. Here we have the major groups of organic material producing organisms in time. And we see that we have typical stuff for the Paleozoic, particularly the lower and middle Paleozoic, which is this part up here, the Architects, Caedinozoans, Scolecodonts. Then we have this part here starting in the upper Paleozoic, going up to recent, which is the whole plant stuff, land plants, which is just starting around the latest Devonian, and the spores and pollen are related to this. And then we have the dinoflagellates right here, which is the modern plankton, or the major modern organic matter producing type of plankton. And we have again the bacteria, algae, and fungi, which are almost present everywhere from Precambrian to today. So besides the paleoenvironments, we also have a stratigraphic control on the type of organic matter that is available to be stored in the sediments. And this is something that we have to keep in mind, because in one of the case studies, this will be very relevant. So how can we classify this kerogen? So how can we describe what type of organic matter we have? These are quite complicated, or not complicated, but complex and detailed classification schemes, biologically based classification schemes for kerogen, which are from the organic petrology and palynology. The organic petrology is mainly this one here, cold petrology systems, and then we have the palynology systems here. And these are mainly based on biological features or biological groupings, and on optical features. So that's the one way to classify the kerogen. On the other side, we can try to classify the kerogen by its chemistry. So if it has these different sources, we can expect also different chemistry. That's what's done by the classical chemical classification of kerogen, the 4 standard kerogen types published and established by Tissot and Welte. We have the 4 types with a typical organic matter. And this is type 1, sapropellic alginate, mainly in marine lacustrine environments, very high hydrogen ratios, low oxygen ratios, and mainly made of lipids and proteins. And this stuff is highly oil prone, producing mainly paraffins, less naphthens. So the kerogen type 2 is mainly planktonic, or is believed to be mainly planktonic. We will see some different ideas later on. But in this chemical classification scheme, it's supposed to be planktonic. It's mainly marine, mainly very typical for most shelf environments. And most source rocks up to date are the sort of type 2, type 3 source rock. The hydrogen index is slightly lower. It's lower than in the type 1. The oxygen ratio is slightly higher. And again, we have lipids, proteins, but also aromatics. And it's still oil prone, but it's a mix of paraffins, naphthens, and aromatic hydrocarbons. Then we get to the point type 3, which is made of humic material. This is terrestrial material. That's what I was talking about. The wood material, the plant debris. It's made of cellulose and carbohydrates, all the products that are developed or that are left over by the decomposition of plants. The hydrogen ratio is, again, is already lower. The oxygen ratio is higher. And this is no longer an oil-prone kerogen, oil producer. It's a very good gas-prone kerogen, a gas producer. And then we get to the type 4, which in several schemes and plots and so on is left out, because this is no longer a hydrocarbon productive kerogen. Therefore, it's sometimes left out in different schemes. This is residual organic matter. From this understanding here, believed to be mainly from terrestrial sources. Also, this can be has to be modified a bit more. with the lowest hydrogen ratios and the highest oxygen ratios, and it's polycyclic aromatics are very present. And the hydrocarbon potential is not at all, it's none, it's barren, it's almost nothing producing. So these are the 4 types of kerogen that we identify in geochemistry. And when you compare this 4-type scheme with the complex schemes that we had seen before, you will understand that here in these 4 groups, several things that are biologically or palynologically are separated are mixed together because it has, from this point of view, a relatively similar chemistry, and therefore it's put together and believed to be more or less the same. How can we identify this chemical composition? So that's a point of geochemical analysis where I just want to flip through, because that's something that most of you will be quite familiar with. So the standard routine analysis method we use for geochemical analysis is RockEval pyrolysis. So we decompose the organic matter by artificial maturation by heating in a helium atmosphere, oxygen-free, and we measure the released amount of hydrocarbons and carbon dioxide. So we do not directly analyze the chemistry of the different compounds that are in the rock, but we analyze the amount of carbon dioxide and hydrocarbons that are set free at certain temperatures, and from this we reinterpret what type of organic matter we have in the rocks. We have the classical peaks during this heating cooling process, the S1 peak, S2 and S3 peaks. The S1 peak is believed to be the amount of free hydrocarbons in the sample before analysis, which gets free immediately when we start heating at very low temperatures. The S2 peak is the volume of hydrocarbons that are generated, the total amount of hydrocarbons that are generated during the full thermal pyrolysis process. So that's the maximum amount of hydrocarbons that can be produced from the rocks, giving used as estimation of the remaining hydrocarbon generating potential in the rock. And then we have the S3, which is the CO2 that gets developed during the thermal breakdown of the kerogen. And from these 3 peaks, we calculate or recalculate different parameters, like the hydrogen index, giving the amount of hydrogen, the relative indirect amount of hydrogen, the oxygen index for the oxygen, the production index, which gives us a level of how much is already produced, or has production started or not, and the transformation index, the transformation ratio, which tells us something about the amount of hydrocarbons from the total amount that are already produced in the current rocks. So these are things that you all know and which are commonly used and seem to be quite simple and work well. But there are some points that we should look on a bit more carefully. Here I have 3 pyrograms from 3 samples. Here's a perfect sample up on the upper left with a nice S1 peak, a very nice developed S2 peak, where we don't have any problems to calculate our parameters that we can afterwards use for kerogen interpretation. But down here we have 2 other groups, 2 other samples, which have a very abnormal pyrogram. So here we have a strong S1 peak, but we have almost no S2 peak. So where's our S2? Somewhere here. Here we again have a strong S1 peak and this bulge. So again, where exactly will we take the S2? And that's a point. The S2 is partially very abnormally developed. So where exactly is the S2 and how can we calculate with such a badly constrained S2 peak? How can we calculate precisely the hydrogen and oxygen conditions in this kerogen? So there's a big question mark on this. On the other side, as I said before, the S1 is seen as the amount of free hydrocarbons, but we had in some studies when we studied the isolated kerogen in RockEval analysis and pyrolysis, we had a strong S1 peak. And in this isolated kerogen, there is no rock, there is no hydrocarbons in the rock, it's just the isolated particulate kerogen. And we still have a strong S1 peak. So S1 does not mean only free hydrocarbons. It's also a part of the particulate kerogen, which reacts under low temperatures that can also build up a strong S1 peak. So be careful if you use the S1 peak as your indicator for free hydrocarbons. What is sometimes very easily done, particularly in unconventional exploration, if you want to know how much, if we have our shales, so how much do we have in the shales? Is there any indicator that we really have gas or oil in place in the shales? And quite often this S1 peak is used as an estimate to see how much is in place in these rocks. And I guess we should be careful with this. So from these parameters, we can now try to identify the different kerogen groups. So Van Crevelen, the clever geochemist, developed this diagram using the hydrogen carbon and the oxygen carbon ratio to define the different kerogen types. Kerogen type 1, the sapropellic stuff, the algal stuff, the type 2 here, and the type 3 here. And we see all this goes down here to the left corner, and these are the maturation trends. So this is immature here, so that's where we start with our kerogen. And the more temperature we get, it goes through the oil window, into the gas window, into the overmature area down here. And the higher the maturation is, the closer these different ratios come together. And if you're here in the gas window, very often we cannot really separate between a primary type 1 and a primary type 3 kerogen because it's all in here. Gives us some problems to identify what it really was, what we are really talking about. So this was the original model to work with. What we normally use today is a modified Van Crevelen diagram, which is the hydrogen index derived from the RockEval data versus the oxygen index. And we see again here the 4 kerogen types, type 1, type 2, type 3, type 4. And it works very well. We have clearly defined the pathways for the different kerogen types, which seems to be pretty nice. But that's theory, and in reality, we get things like this. So again, we have the type 3 trend here, the type 4 trend here, the type 2 and the type 1 trend. And we have some samples that fall closely to some of the pure trends, but a lot of the data are somewhere here in between. So how can we really identify what is this? It seems to be a mixture of type 2 and type 3, but how much type 2, how much type 3, or how does it work? And the same here, we see here, so we have even the type 2, the type 2 to 3, the type 3, even a little bit more detail. But again, most samples are somewhere in between the clearly defined reaction ways, which gives us some more interpretation on the data that to understand what type of kerogen do we work with. So apart from this, more and more in the 80s and 90s and up to date, it has become more and more common to use molecular compositions of the organic matter in the source rocks. And we can use hydrocarbon relevant molecules like here and define with different plots, define the different kerogen types depending on the different molecules. And we can use biomarkers, very famous pristane-fetane ratio, which is very often used to identify a sort of polyenvironmental classification that we can now afterwards can use for an understanding what type of organic matter we can get from these environments. And also here, different types of sterines, which are used for the classification of different environments, and with this also for the classification of different kerogens in the different environments. But again, we see huge areas where we have a quite big variation. So we're not really getting highly precise groupings, which we have a very clear chemistry and a very clear and precise differentiation between all the different types of organic matter that we have in the rock. So Finally, geochemical analysis, to sum that up. All of these methods, and it doesn't matter if you do RockEval, if you do gas chromatography, biomarkers, whatever you do, all these geochemical analyses have one thing in common. They are done on bulk rock samples. So you study the whole lot of organic matter that is stored in the rock at once. And you always get the mix of chemical signals of the mix from this organic matter in the rock and try to reinterpret this. So you have no direct identification of the organic components in the rock. It's all indirect analysis by interpretation of different chemical parameters, molecules, biomarkers, whatever you use. And it's more or less unable to identify and even more to quantify mixed kerogen in your source rocks. And depending on the kerogen mix, your interpretation can lead to significant pitfalls in the evaluation of hydrocarbon potential. If you reinterpreted your parameters in the wrong direction, you might get a completely different, and in the worst case, completely wrong interpretation of the hydrocarbon potential of your resource, and in the end, get a big problem if nothing works out when you start to explore and try to produce this resource. So there is a high risk working only with these bulk rock indirect geochemical analytical methods. So what can we do? What else can we do? We can do optical analysis. So now we switch to the part of optical analysis, which will be the major part of this presentation, because that's a point that is overlooked very often, and there were different attempts to use optical analysis of organic matter for all sorts of purposes, for environmental interpretation, for depositional system analysis, climatic analysis, all this organofuzzy, palinofuzzy schemes, and also for understanding the hydrocarbon potential. So since the late 60s, 70s, people had worked on this, but it never really came through because geochemistry seems to be so easy and so clear and so reliable that there was no really interest to develop better workflows in the optical analysis. But as I've shown before, geochemical analysis seems to be highly precise, very reliable, but in fact, we are working with a lot of interpretations and a pretty high risk of error if you only work with these interpretations. Optical analysis can help us because we isolate the kerogen and then we directly study the actual kerogen under the microscope. So we see directly the kerogen and we can see what it is made of. We can directly identify the organic components in the kerogen, the optical analysis. We can identify if we have mixed kerogen, and this is more than 95% of the kerogens are mixed kerogens, and what sort of mix we have in composition, in preservational features of the different parts of the organic matter, and also in maturation. Our kerogen in one rock sample does not necessarily have to have one level of maturation. In most samples, we have several levels of maturation. And all this has to be understood to make a very precise evaluation of the hydrocarbon potential from this sample in the end. In the end, you can identify from this different kerogen types with different hydrocarbon potential mixed within the total kerogen of one sample. So that's what we look at in optical kerogen analysis. This light gray stuff are some minerals because time is money, so we don't have time to wait until the acids have broken down all mineral residues. So we just leave the sample overnight in highly concentrated fluoric acid to break down all the silicates, all the clays. Before it was a couple of hours in concentrated carbon hydrochloric acid to break down all the carbonates. And then we get out the organic matter, which is not touched by the acids, and some minerals, which are not completely dissolved. So we ignore just this. because we are interested in this brownish to black stuff, the organic matter. And we can concentrate the organic matter on the slide, and then we study this with different types of microscope. So normally we start with normal light microscopy, then we can do fluorescence microscopy and also reflected light microscopy to get all information out of the organic matter that is stored in the kerogen. And as you see here, this is not one type of organic material. You see just by the colors, just by the forms, by the different features, you see that we have very different type of organic material. We have architects, plankton, we have spores, we have prasinophytes, algae, we have vitrinite, wood debris, like this here. We have this structureless brownish stuff, which we call amorphous organic matter, strongly degraded organic matter. We have several of this here. And then we have this black stuff, which we call inertinite, because it's inert, it's highly codified, very carbon enriched dead carbon. It's no longer reactive. So, and this is typical in almost every sample. We have a mix of all different things in our rock sample. And now we can quantify, we can quantify these different particles from our slides. We can make a volumetric analysis of the different particle groups, and we can from this then make an estimate how much of the different kerogen types we have in this sample. And this is a major difference that you have to understand between the geochemical analysis and the optical analysis. In geochemical analysis, one sample has one kerogen type. So we have a sample that is kerogen type 2, or type 2 to 3, or type 3, or type 1, whatever, but each sample is classified into one kerogen type. In optical analysis, we quantify all up to 4 kerogen types within one sample. Most samples have 3, some have 4, all 4, some have only 2. Very, very few samples have only 1 kerogen type in the kerogen. But there is the huge majority of samples has a mix of different kerogen types, and we quantify the different kerogen types in one sample. And this is a much more precise analysis than the bulk geochemical analysis can give us. So how does this look like? We have 3 directions we work on. The first is kerogen composition. The kerogen composition refers directly to the type of hydrocarbons which are primarily generated from the source rocks. And we can, the composition, we quantify the different types of organic matter, organophases, and correlate this into kerogen types. The second point is kerogen preservation, because this also gives us some information on the hydrocarbon potential of the source rock. Preservation gives us an information on the hydrocarbon generation from the kerogen, because hydrocarbon generation causes increasing degradation. So if we produce hydrocarbons from our primary organic material, this material has to get decomposed. It changes not only the chemistry, it also changes its shape, its optical, geometrical features. So you see when you have a spore that is not touched by hydrocarbon generation, very clearly defined, looks like a spore should look like, and you see a totally rotten rest of a spore, which is strongly transformed into hydrocarbons, and just some fragments of organic matter are left over. So this is the effect of hydrocarbon generation on the preservation of the organic matter. So we can use preservation as an indicator for hydrocarbon generation. And the third one is the organic, the kerogen maturation. So of course, besides the composition, also it's important to know the thermal environment that we're in. We get information about the thermal regime of the source rocks. They are productive or not, if we are in an immature or over-mature stage or oil or gas window. So this is pretty important to understand what part of the kerogen can actually produce hydrocarbons. And this kerogen maturation normally is based on vitrinite reflectance analysis and polynomorph color indices, which is a topic that I left out of this presentation because this was included into the last presentation that I gave last fall in great detail. And if you're interested in this particular part, you can find the last presentation on YouTube and check out what I told about this. And if you have questions, you can come back to me and we can discuss this later on. So here we will focus on the 2 points, the composition and the preservation. Composition. So here we have an overview out of an organic matter slide. And we see different components which are coming from different organisms. And we identify the different particles, and then we can quantify the different groups, the palynological groups. And in the second step, so these are the things that we can identify, we put it into palynological based groups, these 4 groups. We see that the different types of organic matter that are part of the 4 groups. And these groups are corresponding to the 4 kerogen types. So we can transfer these groups and the quantities of these 4 palynological groups into quantities of the different kerogen types. Kerogen type 1, 2, 3, 4. Therefore, we see the different quantities for the different hydrocarbon potential. How much is very high oil potential, how much oil potential, gas potential, or no potential. And also this is very important to quantify the amount of inertinite, because this reduces the whole hydrocarbon potential of the sample. So again, as I said before, this third step after the transformation from the palynological groups into the kerogen types, we have all 4 kerogen types quantified in each sample. We no longer have one kerogen type for one sample. We can quantify all 4 kerogen types in each sample. This is a very important difference to the geochemical analysis, and this is also very important to understand when we discuss. So if I discuss with geochemists and I talk about type 2, then I only talk about this part, type 2, the Huttenite group in my source rock, not about the rest of it. The geochemists talk about type 2 if the whole sample, the whole organic matter falls into the type 2 range. So this is something that we really have to be careful how we use the terms. Beside normal light microscopy, we can also use fluorescence microscopy, which is very helpful because the different levels of hydrogen in the organic compounds has an effect on the fluorescence colors. The kerogen type 1 is this bright yellow colors that we see here in the acutags and lyospheres and presynophytes, and amorphous, algal amorphous material. Then we have the kerogen type 2, which is not so strongly bright yellow. And we see right here with the dynasis, we can very well see the difference between type 1, the little acutag here, and the dynasis beside. So this is type 1 and this is type 2. And you see the difference in intensity in the fluorescence. And again here, oh, sorry, coming back. No. So here we have kerogen type 3, the vitrinite. So this brown stuff here is a vitrinite. Here we have an algal presynophyte behind, which is lightning yellow in fluorescence. But the vitrinite itself is brownish in normal light and also stays almost the same in fluorescence. And then we have the last group, which is black in fluorescence. We have the inertinite, which is black in normal light and also stays black in the fluorescence microscope. But we also have other types like zooclasts, like forum linings, so the organic wall linings inside the forums. And this is brownish here in the normal light and gets dark, gets black in the the fluorescence light. And this gives evidence that this is typical also for kerogen type 4. So also these forum linings are kerogen type 4 and not type 3. Also they are brownish in normal light. So this is a very good tool, and it's even better if you have a strongly degraded sample. Here we have two samples made of strongly degraded organic matter, where you can't clearly see primarily structures. So it's hard to identify if this was in its first life a phytoclast or a big pollen grain or anything else. And the same is here. But in fluorescence, we see a strong difference. Here, this strongly degraded particle stays dark, stays black or dark brown. This yellow stuff here is algal, the small algae which is below the particle here. And in the opposite, we see here organic matter which turns yellow in the fluorescence light. So this is amorphous material derived from terrestrial sources, from strongly degraded plant debris. And this is amorphous organic material which is produced from algal blooms, from big algal colonies which are rotten away and are already start to decompose. But we still see the fluorescence colors, because the fluorescence colors are not controlled by degradation, by the preservation. Fluorescence colors are controlled by maturation. So we see the fluorescence up to the end of the oil window, and it gets less and less intense towards the end of the oil window. And then in the gas window, there is no fluorescence in all the organic matter at all. So that's the point. If you have these strongly degraded samples in the oil window, we can very well work with the fluorescence microscopic analysis. If we are in the gas window, this is no longer available. So from this analysis, we can quantify the four different types of kerogen: type 1, type 2, type 3, type 4. And we can quantify all these kerogen types in each sample. So each bar is one sample, and a shale section, which is a black shale from Germany, which was sampled at certain intervals. And we see here oil-prone stuff, the greenish colors. The red colors are type 3, gas-prone stuff, and the black is barren, type 4. So with this, we can quantify the oil-prone versus the gas-prone, the greenish versus the red. And we can quantify the productive part of the kerogen under the given conditions. And this will lead us to the net TOC, to the part of the TOC that is really productive under the given conditions. Because when we measure TOC, it measures the carbon from all parts of the kerogen, so the whole range. But this black stuff here, this is dead carbon. This is no longer productive. This has to be reduced, or the total TOC has to get reduced always by this type 4 stuff, because this is that wherever we are. The rest depends on the maturation. If we are in an oil window environment where these samples come from, only this green stuff is a productive part of the kerogen. All the red stuff, which is pretty much up here, is not productive under the maturation that we have in the area. So then we have the productive kerogen versus the unproductive kerogen, and this will reduce our the amount of productive organic matter dramatically compared to the total TOC. So it's very important to know the net TOC to make a really detailed, reliable evaluation of our resource potential. And we can develop, out of this, we can develop a detailed kerogen composition within the whole source rock unit. And we can identify productive source rock intervals within the total source rock units, and identify less and high productive intervals. So we get a sort of net source rocks definition. And that's something that is well known on the reservoir side for many, many years, where in the classic formations, the net reservoir units are already defined. because these are the really intervals that are of interest. And the same has to be done for the source side. That's something that we also have to do for the source rock if we want to make a step forward for a more precise and reliable source rock analysis. It's not good enough to say, okay, we have 100 meters of shale, so we have 100 meters of source rock, because that's mostly not the case. In this 100 meter, we might have 80 meters, 50 meters, or maybe only 10 meters, which are really highly productive source rocks. And the rest is just shale, but nothing more. And that's something that we have to understand and to identify to get a really reliable and detailed resource evaluation in the end. That's another type of plotting your results from optical Kerogen analysis. This is something I started when I started to work with these ideas. I very often use these ternary plots, but today I have to say I prefer to work with the other schemes, which gives you a much more detailed idea of what you're really working with. The second point, as I said before, is degradation, or preservation, is the decomposition of organic matter from the primary material into the degraded stuff. That's what we see here, a very nice, very well preserved spore, which is strongly altered right here. Here we have a nice phytoclast with the cuticles, and that's what is left over after the degradation. And we have to identify and to differentiate between two types of degradation, because they have very different sources and very different effects. We have the primary degradation, which is microbial and chemical alteration during transport and deposition. And this has nothing to do with maturation and hydrocarbon generation. So this is something that is totally apart from this. It's a very early, happens during transport and early depositions in sedimentary deposition. And then later on, if the deposition is closed, if the burial starts, if the maturation rises continuously, we get into the secondary degradation, which is related to the burial and maturation, and in the end related to the generation of hydrocarbons, because these hydrocarbons have to be produced from these nice organic compounds, and by the development of hydrocarbons, the primary organic matter gets destroyed and we leave something over like this. And that's something I try to assess in this 4-scale scheme here, from well-preserved, slightly degraded, hardly degraded, totally degraded. And this is something, this is really gradual, because when we start with the maturation in relatively low temperatures, in the early to middle oil window, just the type 1 kerogen starts to get decomposed. This very lipid-rich, this very hydrogen-rich organic matter compounds, they start to decompose in the middle, low to middle upper oil window. Then in the middle upper oil window, peak oil window, also the type 2 stuff, the kerogen type 2 stuff starts to get decomposed. All the oil-prone stuff gets decomposed, and we get more and more degradation. That's something, here we see the algal stuff is strongly degraded, so the type 1 stuff is already strongly degraded, but the spores here are well preserved. So this is something, this is a sample from the lower maximum middle oil window, because all the type 2 stuff is very well preserved. And the type 3 stuff, the wood particles here, of course, too. And then we get even higher when we get into the gas window. All the type 2 stuff is degraded, and even the type 3 stuff now starts to get decomposed. And finally, if you're in the upper gas window to the overmature, when we went through the whole maturation process, almost all hydrocarbon particles, or all kerogen particles that can produce hydrocarbons, are decomposed, because we went through the full temperature range and everything is transformed that is able to be transformed. And then we get something like this. And if we have an oil phase in the beginning, we get an even stronger degradation, because we have lots of organic acids in our raw petroleum mix, and all these acids are strongly reactive with the organic matter, so they support the decomposition of the organic matter. And there is more that we should know about preservation. I thought at the beginning I said, okay, the primary degradation is not related to hydrocarbon generation. That's right, but it has an effect on hydrocarbon generation. Because if we have strong primary degradation, we have a low hydrocarbon potential, because the organic matter is strongly decomposed and a lot of components are already away when we get into the maturation into the oil or gas window. So we have a sort of residual organic matter even when we start to produce hydrocarbons, and there only very little hydrocarbons can be produced out of this residual organic matter, which is left over after a strong primary degradation. And the maturation-related secondary degradation indicates if and how much of the productive net TOC has started to generate hydrocarbons. So we can see if or how much of the generally productive kerogen has already been decomposed or start to decompose. So how intense is our hydrocarbon production? And this is what we see in the different preservation levels. We can estimate the intensity of the degradation, and from this estimate the intensity of the hydrocarbon generation, in a way a sort of estimate of the kerogen transformation. This preservation also has a very interesting point particularly for unconventional plays, because the preservation is directly linked to microporosity of the organic matter. The more we decompose the primary organic matter, the more microporosity we get in our organic matter. And this microporosity in the organic matter is the major storage capacity in shale, in gas and oil shales, particularly gas shales, because the organic matter, the organic surface, organic carbon surface, can fix much more gas than the mineral surfaces. So the organic matter microporosity is much more important in these shale plays than the rock matrix microporosity. And here on the right, we see a nice SEM picture with an organic compound here with lots of micropores in there, and which is strongly degraded. And we see here all these pores are still open. So that's an in situ organic component, and all the pores are open. So there's plenty of room to fix gassing. And that's another very important point. If you look for these unconventional plays, we have to analyze the timing of the degradation, because the primary and very early secondary organic matter degradation creates a lot of porosity, but this gets mostly destroyed during the compaction. And when we get into deeper burial and get the full compaction of the shales, shales have a massive compaction. If this is initial primary degradation, all these pores will be completely gone after the compaction. So if you have secondary degradation, we have these pores open. And that's also a good indicator. If you have a polished rock slab and you work with on the SEM, you can identify these open pores. This definitely has to be a process after compaction. So this has to be secondary degradation. This is a very good proof or a very good indication that this degradation here is secondary. And this in situ analysis of organic matter microporosity with the SEM is really essential to really understand and reliably estimate unconventional shale resources. So the benefits of all this, I just want to sum up what we have gone through so far. We can identify and detail quantify each single kerogen type within the total kerogen of each sample, which is a big step forward in detail of the kerogen composition. The quantification of the productive versus the unproductive proportions of the total kerogen leads us to the net TOC, which really gives us the real productive amount of carbon that we have into our systems. So we get away from the total TOC, which can be made of 90% dead carbon. Did one study where most of the samples had more than 90% of the dead carbon, of highly inert organic matter. So the TOC numbers looked pretty good, but after the reduction on the net TOC, there was no need to do any more investigation, because the TOC, the really productive TOC, was so low that there was no really productivity to expect. So that's a very important point, is net TOC. We can quantify the oil-prone versus gas-prone kerogen within the productive part of the kerogen. We can estimate the hydrocarbon generation from the oil-prone and gas-prone parts of the kerogen by the detailed analysis of the preservation of the different kerogen types. Then with the maturation, which we left out of this presentation, we can make a high-resolution analysis of the organic maturation, and best with two independent methods, vitrinite reflectance and polymorph colors, for example. And that with this, we get a detailed paleothermal history and hydrocarbon maturity to fit in our results from composition and preservation. And in the end, we can identify and quantify different kerogen types with different hydrocarbon potential within the total kerogen of each sample of our study. And just to give you an idea, what does it really mean? What is the really difference? Does it really make such a big difference? I just put in this slide from my lectures that I also show the students to make them understand what the really difference is between the geochemical bulk rock analysis and the optical component specific analysis. And here we have a sample with a red star here with a given HC-OC ratio. So this plots directly on the vitrinite trend, and every one of you, if you would get a result like this, you would expect to get 100% gas-prone type 3 kerogen. In fact, that's the result from the RockEval with the Van Crevelen diagram interpretation, but in fact, in the microscopic analysis, we see a completely different picture. We only have 50% vitrinite, kerogen type 3. We have 30% dead carbon inertinite, so we have to reduce our total TOC significantly. We have 15% of exenite, type 2 kerogen, and 5% of alginite. So we have 20% of oil-prone stuff, 50% of gas-prone, and 30% nothing. So different from the expectations from the RockEval analysis, that we just get production in the gas window and totally only gas from the whole sample, we get production even in the middle to upper oil window from this 20% here, followed by the gas production in the gas window and the cracking of the oil if you get in further into the gas. And these 30% will produce nothing. So this makes a whole different story out of the sample. And we could have the same sample just plotting right here with a totally different mix. So it's just a sort of mathematical equations that you see here, how you can calculate. And if you would have a different composition, you could have a very different composition from this, but finally end up in the hydrocarbon, hydrogen-carbon, oxygen-carbon ratio diagram, we could end up at the same plot. So it looks very much the same in the geochemical analysis, but it's completely different if we look into the optical details. And I guess that's a good example to understand what's the difference between the two methods, geochemistry and optical analysis, really is about. So as a cream on top of the cake, we go into the case studies from theory to real life. I will show you some results from a study in the Lower Jurassic oil shales in southwest Germany. In the Lower Jurassic, we are here. So this is part, or is somewhere between the North German, London Jurassic Basin and the Paris Basin. We are here in the southwest German Jurassic part of the basin. And this is a more detailed map, and we see here a sort of topography in this shallow shelf sea. We see some islands, and we see the shallow shelf, deeper shelf, and then we see sort of intra-shelf basin. And this area here, the Kraichgau area, this exactly here I'm sitting at the moment. So directly at the margin of this Kraichgau basin. And we studied 3 wells from the marginal basin compared with outcrops and 1 well from the Kraichgau area. We have, as I said, 2 oil shales, one in the Hettangian, in the very early transgressive phase in the basal Jurassic. So this is an early transgressive shale system, producing already black shales, which I was really surprised of. And then we have the well-known Toarcian black shale system, which is a well-productive source unit in many places of the world. So how does it look like? This is the early transgressive shale. In the basin center, we see a clear black shale, dark gray black milestones, rich in pyrite, bioturbation levels present, relatively high TOC, relatively high hydrogen indices. So that's what we expect from an oil shale like this. And time equivalent in the marginal basin, we have this mix of gray or medium to dark gray marl and mudstones, light gray limestones, and partially sand and siltstones interlayers in there. Pyrite is rare, bioturbation is very common, and the TOC is much lower, and the hydrogen index also. So we see in the early transgressive shale, there's a big difference between the basin center and the marginal basin parts. And we look into the late transgressive shales. Again, this is a basin center, looks more or less like the picture before. And if I would show you the cores, you wouldn't see a difference in the macroscopic features. Again, dark gray black marl and mudstones, really thin limestone interlayers, rich in pyrite, but almost no bioturbation in the whole section. Again, very similar TOCs than before, and relatively even higher hydrogen indices in this interval. And the same interval in the basin margin now also is made of dark gray black marlstones, rarely limestone interlayers, also rich in pyrite, but with a number of bioturbation levels. And we get a significantly higher TOC, very similar to the one in the basin center, and also pretty high hydrogen indices. So we see in the early transgressive black shales, the black shale deposition only takes place in the infra-shelf basin, and in the high stand, this is a widespread system all over the shelf area. So what is the difference between these 2 oil shales? And the question was, we have oil production, it's well known here in the southwest of Germany, it's one of the classical oil provinces of Germany, and it's known that a huge amount of this oil is contributed by the lower Jurassic oil shales. And the question is, do these both intervals contribute the same? Or is there a difference between the lower and the upper oil shale? And does it make sense to extend your exploration in areas where you only have the lower oil shale, or is the upper oil shale needed to have a good prospectivity? So what is a better source, the Toarcian or the Hettangian, or is it the same? Because the lower oil shale has a much wider extent, so you could extend your exploration if it's really related to this lower oil shale deposit. So we did RockEval analysis, and we see 2 groups of data right here. The red one is the lower interval, this is the upper interval, and we have mainly Kerogen type 2. Unfortunately, we have done much more samples, which I can't show you because they are all industry data, but they are all plotting somewhere here in a very mixed field. So the majority of data is here in this mixed interval, and it's a sort of mainly Kerogen type 2 stuff. So the lower interval is mainly made of Kerogen type 2 with a tendency towards 3, and the upper interval is Kerogen type 2 with a tendency towards type 1. But in general, both are mainly made of Kerogen type 2, what we call Kerogen type 2, and have a relatively mixed field here in the middle. So from this, RockEval would tell us, okay, they are mainly very similar types of Kerogen in both shale intervals, and so they should both contribute to the current oil systems. In optical Kerogen analysis, the lower interval, I realized that it's strongly dominated by amorphous organic matter, so-called AOM, which is very often classified as Kerogen type 1. But in fluorescence microscopy, it turned out that this, you see this particle here that you have seen before, that this amorphous organic material in the lower interval is dark in the fluorescence. So this is definitely not type 1 Kerogen. This amorphous organic material is mostly non-fluorescent, more than 95%. So these are the relics of terrestrial, totally degraded plant debris that was spilled into the system in huge numbers. And this produces a very nice gas-prone Kerogen type 3 dominated system, but not oil-prone Kerogen type 1 dominated system. And that's the reason why we have here in the basin center, where we have mainly the amorphous organic material. We have almost no amorphous organic material here at the basin margin, where we have this huge amount of type 3 Kerogen, which is all made of this strongly rotten terrestrial stuff that gets into the basin, and which is this non-fluorescent amorphous organic material. And we get a very high gas potential in the basin center in this black shale. In contrast to the basin margin, has a mix of oil-prone and gas-prone and barren Kerogen. The barren part, the type 4, is up to 20 to 35%. So this strongly reduces the net TOC compared to the total TOC. And because of this, the relatively low TOC numbers get even lower for the net TOC, and we get a very poor mixed hydrocarbon potential out of the rest that is here in the samples, and a very high gas potential in the basin center. So that's the lower oil or black shale. The upper interval is also dominated strongly by amorphous organic matter, as we see here, different pictures. And the AOM is also mostly fluorescent. So here we have more than 90–95% of fluorescent amorphous organic matter, which is indicating that this is Kerogen that is from marine algal material, which is highly oil-prone Kerogen type 1. This is really Kerogen type 1 amorphous organic matter. So this will lead to a totally different picture. And we see here, again, the basin center and the basin margin. And we see here again the area with this huge amount of amorphous organic material, which is mainly highly oil-prone Kerogen type 1. And so the whole system is a highly oil-prone, oil-producing shale system. And the net TOC is very similar to the total TOC because the inertinite, the type 4 Kerogen, is very low. It's about 10% maybe. The basin margin again shows also in the lower part very high oil-prone material. Also here this type 1 stuff is made mainly of amorphous organic matter, and then we get a stronger terrestrial influx in the upper part of the shale section, and we get again more terrestrial stuff in. But here now in the late transgressive shale, we also have in the basin margin high potential oil system. So putting these things together, the lower interval and the upper interval, just by the color code, you see we have a totally different system. So we see here the TOC, which is well to good, also very good in the upper part. So we have high quantity of organic matter. We see very bad preservation or very poor preservation, so a lot of degradation in both intervals. And we have very similar maturation because there's not so much section in between these two intervals. So we have a very similar maturation in the middle to upper oil window in both intervals here in the southwest German area. But this one is a highly oil-prone system. This one is a highly gas-prone system. So here down in the lower black shale, we have a potential high gas potential, a theoretical high gas potential, which is not active with this low maturation. While in the upper part, we have a strongly oil-producing system, which has produced or started to produce significantly under the given maturation in the middle to upper oil window, and we have a very high hydrocarbon potential, oil potential in the upper part. So bringing together the composition and the maturation tells us these oil systems, the Jurassic oils here in the southwest of Germany, are contributed only from the upper part, or almost completely only from the upper part, with very, very little minor amounts from the lower part, because the lower part is a gas-producing system which is not active under this low maturation. So coming back to the initial question, it doesn't make sense to extend the exploration into the areas where we only have the lower black shale, because we will find no production. So the oil production is controlled by the upper interval. So this was a first case study, and we switch on to the second case study. A totally different scenario, totally different time, no longer the Jurassic. We get back into time, into the early Paleozoic, and look at the hydrocarbon potential of Silurian to Ordovician shale systems in northern Poland. Not long ago, just a couple of years, there was a big jump into Poland, into the so-called shale belt. All the international companies jumped in because there was a huge expectation of high resources in the early Paleozoic shales, particularly the Silurian shales, in Poland as a major shale resource system. And as we all know, the big storm calmed down. The big international companies jumped out, and now there are some national companies which are trying to go on with exploration in specific areas. So the expectations weren't really kept by the results from the exploration. There is a lot of shale across Poland in the early Silurian, also in the upper Ordovician, but there's not a lot of gas in the shale. So what is the problem? This was the reason to have a closer look on these early Silurian shales. These are the 4 wells that we studied, and we see mainly shales and milestones were studied. And that's what we get out. We get relatively low TUC values between less than 1% up to 2, 2.5, rarely higher than 2.5%. And we get Tmax temperatures, no, this is the SCI, the spore color index, with a very low maturation. And RockEval analysis told us that we have something between type 2 and type 3. Same here, tending more to type 2. Here we have something between type 2 and type 3. So this is what we get out of geochemistry. And in fact, geochemistry and a bit of optical analysis, because this already was the first part of the study we did, because we are in the Silurian. Now we come back to the very beginning. I told you the land plants did not appear before the end of Silurian, early Devonian. And vitrinite is produced from land plants. It's a woody part of land plants. So in the early Silurian, we have no vitrinite to analyze maturation, which is a big problem in many early Paleozoic plays. We have no vitrinite, and therefore we have lost the most reliable and best established maturation parameter that we normally can use. So in this case, I started to use polynomorph colors. We have acritax, we have cryptospores, and just by the color range, we can make an estimate of the maturation. And before there were mainly maturation done by Tmax, which indicated much higher maturation. And with this proposed to be high maturation and this poor TOC, the idea was, okay, this is pure TOC because most of the TOC is already transformed into hydrocarbons, mainly gas. So this is a perfect gas play. Now we see here, the first point, we have not really mainly type 3 gas-prone material, but we have a mix of type 2 to type 3. And this again becomes a problem because kerogen type 2 and type 3 are mainly derived from land plant material. Type 3 is all the woody parts of the plants. Type 2 is mainly derived from plants, again, from pollen, spores, wax-rich components, leaves, and parts of plants, and only dinocysts. Dinocysts are the only component that is part of kerogen type 2. And all this terrestrial plant stuff is not available in the upper Ordovician and lower Silurian because we have no land plants. So what is this kerogen really made of? Why do we have such a strong kerogen type 2 and 3 signature? Also, we have no real type 2 and type 3 kerogen at that time. How does this work together? So we looked into detail into the kerogen with optical analysis, and we found out that we have type 1. This is a light yellow stuff. This is all type 1. And then we had this gray stuff, which is mainly dark brown degraded organic material, which is not really understood what it is really, where it really comes from. But from the fluorescence color, it seems to be more type 4 than type 3 kerogen type. So this was, the first attempt was with normal light. Then we switched to fluorescence light, a fluorescence microscope, and we changed the whole system. You see here, now with the fluorescence microscope, with a strongly degraded material, we had a lot of samples with high amounts of fluorescent amorphous organic matter, which showed us that we have a lot of samples with relatively high amounts of oil-prone type 1 organic matter, type 1 kerogen, and we have this type 4 stuff. And in the fluorescence, this is mostly black. So this is very clear evidence that this other structureless degraded organic material represents more type 4 than type 3. So the type 2 and type 3 that we see in the RockEval analysis is in fact different mixtures of type 1 and type 4. And now we go back to the example I showed you before, how we can calculate the hydrogen and oxygen ratios from the different mixtures. It's just a mathematical issue to recalculate different hydrogen and oxygen ratios from these different mixtures. And depending on the mixture, how much type 1, how much type 4 we have, we will get a sort of something ranging between type 2 and type 3. A sample like this will tend strongly to type 3. A sample like this will be almost type 2. So in fact, the type 2, type 3 that was proposed to be the major component changes completely. And in fact, we have a mix of type 1 and type 4. And again, this type 4, because as I showed you, we are just in the early to middle oil window, all this gray stuff here is dead carbon, is unproductive TOC. Only this yellow stuff is productive TOC in this. And therefore, the net TOC gets sometimes much, much lower than the total TOC. And the total TOC was not even relatively high, so quite a number of these samples are almost unproductive from the really net TOC based productive amount of carbon in the samples. So this turned around the story completely, and you could understand why all these companies were drilling like crazy all through Poland and didn't get anything out. First, the maturation was wrong. It was not in the gas window, but in the early to middle oil window. And then second, the kerogen was wrong, and there was much less productive kerogen than it was it's opposed by the interpretation of the biochemical data, particularly the TOC data. So this just as a second case study, how much you can add with optical analysis to your standard chemical analysis to understand the difficult and complex systems. I gave you, I guess, already all the information. The question in this discussion in Poland was, so what are the future targets? And the future targets have changed completely. You don't have to search for a shale gas any longer in Poland. You have to search for shale oil. If you're lucky, you get shale oil, but never shale gas. So you have to identify the lithophascis types, which are rich in kerogen type 1, with a relatively high kerogen quantity, so relatively high net TOC values, in areas of maximum maturation that you get at least into the middle oil, better into the upper oil window. And these are the targets that you can search for along the shale belt. And this is done with some companies, mainly national oil companies, up to now. So these are the two case studies. With this, I'm finished now. Thank you very much for your attention. If you want to have more information or want to discuss more, you can check out my homepage, or you can contact me directly via email or Skype or whatever, and we can discuss all your questions later on. Thank you very much.
Yeah, thank you, Hartmut. Again, and I'm glad you managed to cover the second case study this time. It's interesting.
I tried my best.
Are there any questions from the audience?
No.
They're all overwhelmed by all the different informations.
I don't know, are you going to ask a question, or are you just laughing?
I'm just laughing.
Laughing, okay. All right. Well, during the first session, we talked about the process of sample preparation, and Hartmut covered it in this presentation. So, but let me just quickly remind myself. Hartmut, what were some of the questions that we discussed in the morning? Remind me. Do you remember? There was something about the potential alteration of the composition of the particles that I was asking, by the sample preparation technique. Can you comment on it again, just for the benefit of this audience?
Yeah, that's right. So when we want to isolate the kerogen out of the rock, we have to destroy the rock completely. So what we use is a double acid treatment, first with hydrochloric acid and then with hydrofluoric acid, and then we break down all the carbonate and silicate structures. So what we leave is all the organic matter, from the very, very, very fine, almost amorphous particles to the bigger particles that I showed you in the picture during the talk in the slides. So if we would take all this organic matter, we would get a wonderful, continuously brownish slide, because all this very, very fine amorphous organic matter would make a brown curtain about all the rest, and we wouldn't see anything. So we couldn't do any analysis. So what we do is we sieve the organic residue after the acid treatment. And we sieve it with a very, very fine mesh size. In our case, in the lab, we use 11 or 15 micron mesh size. So we really get rid of the very, very fine particles. And there was a question if this might change the composition, because people, we were discussing, okay, this is amorphous material. So amorphous material has a certain chemistry, certain hydrocarbon generation potential. So by the filtering, you change the composition of your kerogen. In one study, we did a test of all 50 samples. So we analyzed the 50 samples whole rock with RockEval, And then we analyzed the isolated kerogen out of exactly the same samples after the acid treatment. And the RockEval results are, apart from 2 samples, are almost exactly the same. So during this filtering and getting rid of this very fine-grained material, we do not change the composition towards one direction. We get just rid of the very, very fine-grained stuff from all the different kerogen types. And I did from one sample, I took some drops, put it on a slide, and went to the SEM, because you can't identify anything in the normal microscope. So we did some look at the SEM to see what really is the stuff that we have in this very fine-grained material. And it's, in fact, it's really the very fine-grained part of all different kerogen types that we have also in the bigger particles. So that's a very good proof now. We don't change the chemistry, the composition of the kerogen during the filtering process.
Okay. Yeah, so the main learning I take away from this is that basically, unless we have samples from the actual kitchens where hydrocarbons came from in a given petroleum system, and we mostly don't have that, we have to model it in a basin model. We have to model the source rock in a basin model with a range of kerogen types, always assuming that we just don't know what sort of kerogen type we would have there. And so in order to capture the potential products and the kinetic behavior, we just cannot fiddle with a simplistic single type kerogen. We always have to assume a mixture and a range of potential compositions of the kerogen.
Yeah, I guess that's a major point. We have to get away from the idea that one sample is one kerogen type. Because more than 95%, far more than 95% of the samples I worked on during the last 7-8 years are made of mixed kerogens. And really, mix means from highly oil prone to dead carbon inertinite, everything in. So the idea that we have one kerogen that is modeled with one modeling approach is surely, in my opinion, far away from reality.
And the second learning is that even with the kerogen classification based on depositional environments that Pepper and Corvey developed in the mid-90s, we still don't know exactly what type of kerogen those organophases represent, because we can be in the center of the basin, or not on the center, in the center, but on a margin, and at one point we may have, no, actually you showed in the center that you had type 3 here, right? Almost entirely terrestrial material that you would actually expect rather near shore. So it's kind of counterintuitive, all that, and we can never really assume what sort of type of kerogen we would expect there, and how that actually maps onto the Pepper-Corvey system. It would be something interesting to follow up on and try to map these two onto each other.
Yeah, that's the point, because this is completely related to paleoenvironments, and we can have very different kerogens in more or less the same paleoenvironments. Or generally the same paleoenvironment, proximal Shale, for example. We can have very, very big differences in the kerogen composition. And the point is, we don't know where we have what mix. Just as I showed the example, we have this data plot that seems to be 100% pure type 3 kerogen, so no doubt about it from our thinking so far. And then we look into it and see, no, it's something completely different. It's a mix of oil prone, gas prone, and barren. So it's not even the strange dots that don't fit to any trends, which are the complicated ones. Maybe they are even easier because we realize that there is something going on. But the ones that really fit very well to the given trends of the type 1, 2, 3 kerogen types are maybe even more dangerous because we think we know what it is, but in fact we don't.
Yeah, I agree. Okay, I think we have exhausted everyone. It's 6:30.
Yeah.
So let's just conclude this session. As usual, I will process these videos and put it on YouTube and announce when this happens. And yeah, thank you all for the attention, for the attendance, and thank you, Hartmut, for presenting this. I really enjoyed it.
Okay, thanks a lot.
Right, good evening, everyone,
Yeah.
or good day in the Americas.
Yeah, enjoy the day in overseas. Exactly. Okay, bye.